A space elevator, the replacement for rockets, is a massive jack-in-the-beanstalk-like structure that would reach up into space from Earth's surface. While it's too tempting a target, it is impossible to defend considering the technological, logistical, and political hurdles in play. The proposed alternative is a cable that goes from ground to geostationary orbit nearly 36,000 kilometers away and holds itself there. Once anchored and counterbalanced, laser-powered climbers would mount the cable, bringing their precious cargo into space. The cable is dropped from a satellite cast into geosynchronous orbit. That is the altitude where the satellite orbits precisely once every 24 hours, so it stays at the exact location in the sky all the time. Gradually lower the long cable from the satellite down toward the Earth's surface. When the cable arrives on the ground, you tie it down. Now you can use the cable to build an elevator cab just like the elevator in a building, and it can slowly go up the rope until it is in orbit. This would be much cheaper than a rocket. Once built, space elevators could carry loads into space for $500 a kilogram, compared to the current price tag of around $20,000 a kilogram, according to a recent report by the International Academy of Astronautics, IAA. But the cable itself is a problem, considering there is no material strong enough to hold its weight over that distance. Nothing in sight is strong enough to do it, not even carbon nanotubes. So there's nothing strong enough to support the cable's weight plus the weight of the cab. If you start looking at materials, the strongest ones are too heavy, and no matter how thin or thick you make the cable, it can't support its weight. As you look for lighter materials, they get weaker and still can't keep their weight. To get this to work, you need a large mass in orbit, either a space station or a small asteroid. The mass has to be large so that it doesn't get pulled out of orbit every time something climbs up the cable. A counterweight at the upper end keeps the center of mass well above the geostationary orbit level. This creates enough upward centrifugal force from Earth's rotation to fully counter the downward gravity, holding the cable upright and taut. To avoid breaking a cable that long, even the most robust material like Kevlar would have to be super thick. There's more weight hanging below with thicker cables, which means the higher parts of the line must be even broader to reinforce the cable. It's a compounding problem that seems nearly impossible. Only if we figure out how to use some super strong and lightweight material like carbon nanotubes will we have a future with a space elevator. Even with nanotubes, theoretically, a carbon nanotube cable could barely support itself plus a reasonably lightweight cab, providing the cable was in one long continuous piece, and you could taper the thickness of the cable so it's thinner at the bottom and thicker at the top. For a while, this looked technologically feasible, although the longest carbon nanotube ever made was just a few millimeters long. If a cable capable enough were delivered, there'd be a risk of a break. If a break occurred at a higher altitude, up to about 25,000 kilometers, the lower portion of the elevator would fall to Earth and drape itself along the equator east of the anchor point. In contrast, the now unbalanced upper part would rise to a higher orbit. Possible or not, risk or not, at least a couple of companies have started with the idea of working on this. And there is a lot of enthusiasm for it. There have been 3 detailed concept designs issued in the last 12 years. First, Brad Edwards and Eric Westling, in their 2003 book Space Elevators, envisioned 20-ton payloads powered by Earth-based lasers traveling at $150 a kilogram, and with a construction price tag of $6 billion. The IAA's 2013 design then equipped their vehicles with more excellent protection from the weather for the first 40 kilometers and drove them with solar power after this distance, allowing transport at $500 a kilogram and costing $13 billion for the first pair. Previous proposals for the counterweight needed on the space end of the cable to keep it tight have included a captured asteroid. The IAA report says this might become an option one day, but is not possible shortly. Experts say this type of setup could be built with current technology. Cost estimates range considerably from $1 billion to $90 billion. Companies in China and Japan have high hopes to build such elevators by 2045 and 2050 respectively. Japanese researchers have even tested miniature prototypes in space. You'd go into an ocean platform from the space elevator, climb into a module, and feel it start moving. You'd see the Earth fall away. In just a half hour or so, you'd pass through the clouds and begin to see the curve of the horizon. Another half hour to an hour later, you'd be in space. You'd see stars, even in the middle of the day. Eventually, you'd be weightless. It'd be a very smooth ride, there wouldn't be any shaking. But getting a first-hand experience of this ride would take a lot of time and money. However, as with all great enterprises, it's just a question of dealing with the challenges one at a time and reducing the risks bit by bit. If built eventually, the best place would be along the equator, at a place with high elevation. Anywhere else would have the cable be slanted at an angle, and will have to be longer and withstand additional tension. While the location has been set for this technological wonder, the detailed mathematical work on the nature of the cable revealed that the cable would evolve to be unstable, whipping around like crazy. The only known way to stabilize would rapidly put you back into the realms of the impossible, or at least the highly improbable. That is, to put rocket motors at intervals along the cable. Even if we overcome the considerable engineering challenges in building this thing, it is terrifying to picture a giant cheese wire scything through space, taking out space vehicles, and being hit by all the space debris already up there. All this said, the space elevator shouldn't be ruled out. Not entirely. At least not on Earth. There's another option. One that was devised by the American engineer and space scientist Jerome Pearson. While it doesn't make much sense for Earth, the Moon is a different situation entirely. The Moon's rotation speed might seem to cause a problem, but what can be done is build a different kind of elevator that you could anchor to the Earth's gravity field. A cable would be run from the Moon and out through the L1 Lagrangian point. From there, it would be dropped down into Earth's gravity field, with a large counterweight secured to its end. And as for the materials required, the Moon is a different matter. Nanotubes leave the scene for the Moon. Materials with higher strength would mean more of the ratio for hauling stuff on the Moon. There could be a configuration with an endless loop of the cable running from the lunar surface and back. Then payloads could be clamped onto the thing, and a 15-megawatt power plant will pull up around 1,000 tons daily. While it doesn't solve our payload problem here on Earth, space elevators make the best sense for building something on the Moon. If it is possible on the Moon, it has to be possible somewhere else too, right? Somewhere like Mars. But sadly, no. Materials for an Earth elevator are at least one order of strength too weak at this time. Mars's gravity is around 0.378 of Earth, so materials are still too soft. So Mars too is opted out of space elevators. While there are solutions to all the problems that could work out, the trouble remains the same. The strength of materials in any setup is finite. So the space elevator concept still comes up in discussions quite a bit, but the truth is that the idea is dead. That's all for today. If you enjoyed this video, let us know what would you like the next video to be about. I'll be reading you in the comments. See you soon.